Linear independence is a special property where each vector in a set is independent of the other vectors. We can say this is true when the linear combination a1, v1, all the way till an, vn, where the a's are just scalars, equals the zero vector. The only possible solution is the trivial solution, where all the coefficients, so ai, are equal to 0. Of course, this generates the zero vector. On the other hand, if we had repetition, so the exact same vector twice, or if we had a scalar multiple of the vector, this would be a bit redundant because this vector wouldn't bring a new direction. If we consider R2 as our space, if we had one vector, let's call this V1, and V2 was just the same vector in the opposite direction, the vectors aren't independent, because if we said A1 V1 plus A2 V2 equals the zero vector, we can generate this by doing, since they're exact opposites of one another, 1 v1 plus 1 v2 equals the zero vector. So two coefficients do not have to be 0 to generate the zero vector. These vectors are linearly dependent. It would be impossible to generate any values off this line. Say if you were trying to get over here, we have no vector going in any other direction besides on the line. Linear dependence, we can say, is the opposite of linear independence. It's where there exists a non-trivial solution to this same equation. Let's check if these vectors are independent in P2. First, let's write them as a linear combination. A times 1 plus x plus b times 3x plus x squared plus c 1 minus x equals the zero vector. And let's see what the coefficients are. Are they all 0? Or is there another possibility? In which case they would be dependent. The zero vector in P2 would be 0 plus 0x plus 0x squared, just the constant 0 polynomial. And let's group together the constants, the x's, and the x squareds on the opposite side. So we end up getting a plus c plus a plus 3b minus c x plus how many x squareds? Bx squared. Now we can say a plus c equals 0, a plus 3b minus c equals 0, and b equals 0. And now let's solve for a, b, and c. Well, we already see b is 0, so let's plug that into the second equation. We get a minus c equals 0. Let's solve for a. A equals positive c. If we move it to the opposite side, we add c. And in the first equation, we get that a equals, if we move the c to the opposite side, negative c. So now we have a equals positive and negative c. So what number is that possible for? That's only true if a is 0, right? And if a is 0, then c equals 0. So we can see that there is only the trivial solution where a, b, and c, all the coefficients are 0. Thus, this set is independent.